Hello everyone, I'm Fei Long, a PhD student from Tsinghua University. Today I'm excited to share our work on Wormhole, supercharging packet-level network simulation of large model training via memoization and fast forwarding. This is a collaborative effort with Zhongguancun Laboratory and Huawei. Now let me begin by setting the context. In recent years, with the rapid development of large models, model parameters have exceeded the TB level, and the scale of corresponding GPU clusters has reached the millions. Leading tech companies have also gradually increased their investment in AI infrastructure, reaching the order of 100 billion. So to verify the cluster hardware designs, such as the cluster topology and interconnect schemes, as well as the most efficient strategies running on these clusters, such as training parallelism strategies and collective communication algorithms, we need simulators to provide low-cost solutions. So the packet-level discrete simulator, PLDES, is the predominant tool for LLM training simulations. Pure packet-level simulators simulate the packet transmission process through networks at fine granularity and support diverse configurations, showing high fidelity and high generalizability. However, during the simulation process, a discrete event on the order of 10 to the 12 can be generated. With the increase in cluster scale, the time cost also shows an exponential growth trend, and it takes several weeks to complete the simulation of large-scale clusters. Currently, there are two categories of technologies that aims to optimize the speed of PLDES, the coarse-grained modeling and the parallel and distributed DES. In coarse-grained modeling for networks, flow-level simulators and analytical models solely calculate the flow rate at the network stability, while AI-based methods employ deep neural networks to approximate network performance at different granularities. Both of them ignore key packet-level events that contribute to the performance fluctuations, causing large error during simulation. For parallel and distributed DES, we call it PDES, and they enable parallel execution of PLDES using multiple cores or machines while keeping packet-level simulation granularity. When it achieves a certain speedup, the acceleration effects exhibits sublinear scaling as the number of the CPU cores increases, eventually reaching an upper bound. At the same time, there is an opportunity cost. The same CPU cores could otherwise run multiple independent experiments in parallel. So to quantify these limitations, we conduct experiments comparing existing simulators. We evaluated them on simulation speed and accuracy respectively, using LLM training workloads with network scaling ranging from tens to thousands of GPUs. So for the coarse-grained modeling, while they simulate fast, they sacrifice accuracy for speed, producing an error margins of 10% to 25%, which is not acceptable for precise network design in LLM training. On the other hand, PDES has the same fidelity as NS3, but achieves sublinear speedup with an upper bound as core increases. This brings us to the key research question of our paper. How can we reduce the computational burden of PLDES while maintaining packet-level modeling and high fidelity? This is the central question that motivates our work on Wormhole. So to answer the question, we analyzed the traffic characteristics of LLM training and made two key observations. The first observation is about steady states in LLM training. A steady state refers to a temporal interval during which flows exhibit stable transmission behaviors. So as shown in this case, when a new disruptive event occurs, such as a flow entering or exiting, the flow rate becomes fluctuating. After congestion control algorithms converge, the flow rates stabilize and exhibit only minor periodic oscillations. The simulation of these repetitive regimes is computationally redundant and can be safely skipped. So as shown in this figure, dense models and MOE models exhibit about 98% to 99% steady-state proportion. Our second observation is about repeated flow patterns in LLM training. A flow contention pattern is described by the set of flows that have overlap as well as the links they travel through. We observe that in LLM training, under a fixed parallelization strategy, the same collective communication tasks are invoked multiple times in one training iteration. Thus, the same contention patterns reappear, as shown in this page. So, for example, in a single training case, we found over 65,000 of flow contention pattern instances, but over 60,000 redundant occurrences. This massive redundancy presents a significant opportunity for optimization through memoization. So the key insight is these simulation events can be skipped with a negligible error. So based on these concepts, let me introduce the overall architecture of Wormhole step by step. First, given the topology and configurations, Wormhole performs port-level network partitioning, which divides the flow into several disjoint sets. So to implement our optimization, we need to identify the flow patterns and find as many steady state as possible. We define a network partition as the network subset for the flows sharing the same port or link, along with the ports and links these flow traverse. As shown in this example, flow 1, 2, and 3 sharing the same common link, while flow 4 and 5, flow 4 and 6 share a same link. So building on the concept of network partitions, we can see that these flows form two different partitions, and the network is separated into disjoint parts. This separation increases the probability of finding steady states because it allows us to identify and process steady state at the partition level, rather than waiting for the entire network to stabilize, which would be extremely rare. So after forming the new network partitions, Wormhole queries a simulation database to check for the existence of simulation results. If the query hits, the Wormhole bypasses the transient phase and transitions directly to the steady-state process logic using the query result. If query misses, Wormhole proceeds with packet-level simulation. So for the unsteady states, we utilize memoization mechanism to accelerate it. We define the flow confliction graph, FCG, as the central abstraction for representing network partitions in unsteady states. Which is an undirected graph. So verticals represent flows, edges denote link sharing dependencies, vertex weights corresponding to the instantaneous flow rates, and the edge weights represent the number of overlapping links. So when a partition enters an unsteady state, the simulator constructs an FCG characterizing its starting condition. After the unsteady state ends, the simulation database records the FCG at the end along with the aggregated transmission volumes and the convergence time. In subsequent simulations, when new partition is formed and the simulation query matches, the costly convergence phase is bypassed entirely. So during the packet-level simulation in query miss, Wormhole employs a steady-state identification algorithm to determine whether the partition has reached a steady state. If a partition enters a steady state, Wormhole skips this period. Otherwise, it continues with packet-level simulation. When the flow ends, if Wormhole misses in the previous query, it memoizes the simulation process into the database for subsequent simulations. And finally, Wormhole continues to process the interrupting events such as flow entering and exiting. So for the steady states, we fast forward them. So in this picture, the green lines represent the real steady state. So for steady state identification, we monitor the flow sending rate using a sliding window. We then calculate the relative fluctuation of the flow rate within a monitor interval. When it drops below a predefined threshold, the flow is identified as in steady state. We then use the average rate within this interval as the estimated rate during the steady state. So we proved that the relative FCT error introduced by this technique has a theoretical upper bound. Specifically, it is smaller than the predefined threshold. So for the fast-forwarding implementation, we use port-level packet pulsing to maintain the buffer occupancy and timestamp offset modification to skip the simulation process without reconstructing its underlying architecture. So let's go through an example to illustrate how Wormhole accelerates simulations. So here is a dumbbell topology with two flows from left to the right. One is a large flow and the other is a delayed started short flow. So when the long flow A started, the Wormhole queries the simulation database and the query misses. The Wormhole then executes normal packet level simulation for this unsteady state period. Then flow A enters a steady state. Wormhole's steady state identification algorithm detects this and triggers fast forwarding. Now the short flow B starts and forms a new partition together with A. Wormhole again queries the database. Suppose this time the query misses again. Then Wormhole executes packet level simulation for this new unsteady state. After this second unsteady state, the partition enters a steady state. The Wormhole detects this and fast forwards through the steady state period again. Then flow B finishes, the partition is changed, and the Wormhole queries the database. Suppose this time the query hits, and Wormhole can completely bypass the unsteady state simulation and jump directly to the simulation steady state. So after the memoization hits, the flow is in a steady state and Wormhole fast forwards through this period as well. So at last, the Wormhole skips the vast majority of simulation events. Implementation. The Wormhole is implemented in C++ based on NS 3.17, constructing of thousands of lines of code. Importantly, Wormhole is fully orthogonal to multi-threading optimization methods. We integrate with Unison by forming logical processes according to the network partitions. Evaluation. We evaluate Wormhole on 4 key questions. Is it fast? Is it scalable? Is it accurate? And is it sensitive to parameters? We compare the Wormhole and Wormhole plus Unison with current simulators. The workload consists of a single training iteration of GPT and MOE models with EP, DP, and PP flows on various models and cluster sizes. So as for simulation speed, Wormhole improves simulation speed by 227 times to 745 times for GPT workloads and 135 times to 510 times for MOE workloads under HPCC. When combined with Unison, Wormhole and Unison achieves a peak of over 1,000 times. Furthermore, Wormhole achieves high acceleration across different congestion control algorithms, demonstrating its broad applicability. And breaking down the speedups, we found that the skipping steady states alone yields the speedup exceeding 130 times for GPT and 50 times for MOE training, while skipped event ratio more than 99%. Memoization for unsteady state provides an additional 1.93 times to 8.43 times speed up on top of steady state skipping. Regarding overhead, the memory cost is comparable to NS3 and the extra database storage cost is less than the MB level. So as for accuracy, the average FCT error is less than 1% compared with the NS3 ground truth across all network sizes, workload configurations, and CCAs. For sensitive analysis, Wormhole exhibits insensitivity to its two parameters. When monitoring in other metrics such as in-flight bytes and queue lengths, Wormhole also works. On other topology like clause and fat tree, Wormhole also exhibits high performances. So to summarize, PLDES is crucial for modern LLM training infrastructure, but existing approaches face fundamental trade-offs between speed and accuracy. As for the current two categories of acceleration methods, coarse-grained modeling suffers from significant errors, while PDS yields limited speedup with an upper bound. Wormhole takes a fundamental different approach by reducing the computational load with PLDS while maintaining packet-level modeling and high fidelity. Result shows that Wormhole achieves substantial speedup exceeding 1,000 times at peak. So looking ahead, we see several future directions, including more memory-efficient simulations for scaling and support for more categories of workloads such as inferencing and post-training and self-adapted hyperparameter settings and so on. And this is the end of my presentation. Thank you very much for your attention, and I welcome your questions and comments.